we will now talk about measurable sets. Okay, so definition. So let X be a non-empty set and H a hereditary sigma ring on X, mu star an outer measure on H. Let E belong to H. It is said to be mu star measurable. We want to say measurable, but we want to say with respect to what outer measure, and therefore we say mu star measurable so that we have no confusion. So it's mu star measurable if for every A in H we have mu star of A is mu star of A intersection E plus mu star of A intersection E complement. Okay, so you see A is the disjoint union of A intersection E and A intersection E complement. So for every set A, if you write this disjoint decomposition, then mu star acts like a measure. Therefore you say that the set E is measurable. Okay, so that's the reason for that. Now remark, by subadditivity we have that mu star of A is lesser or equal to mu star of A intersection E plus mu star of A intersection E complement. Therefore mu star measurability is equivalent to showing for every A in H we have mu star of A is greater than or equal to mu star of A intersection E plus mu star of A intersection E complement. Okay, so this is so it's enough to check this. The other inequality is obvious. So now we start with a nice proposition. So X non-empty, H hereditary sigma ring, and mu star outer measure on S. Let S bar be the collection of all mu star measurable sets. Then S bar is a ring. So in particular, you know that the empty set is always there. So that is of course obvious, because mu star of A is A intersection phi is A, empty set, that is 0, and A intersection phi complement, which is whole of X, is just A. So this equation is always true. So we know that empty set is always mu star measurable. Okay, so proof. So we want to show that it's a ring. So that means we have to show that it is closed under unions and closed under differences. So let us take A in H and E and F in S bar. They are mu star measurable sets. So we want to show, to show E union F belongs to S and E minus F also belongs to S. Okay, so this is what we need to show. For arbitrary A, we have to show one of those properties above. So we know that mu star of A equals mu star of A intersection E plus mu star of A intersection E complement, because E belongs to S. Now mu star of A intersection E can be written as mu star of A intersection E intersection F plus mu star of A intersection E complement intersection E intersection F complement. This is because F is a measurable set. Okay, then mu star of A intersection E complement is in the same way mu star of A intersection E complement intersection F plus mu star of A intersection E complement intersection F complement. So if you now substitute for these in all that, so you get mu star of A equals mu star of A intersection E intersection F plus mu star of A intersection E intersection F complement plus mu star of A intersection E complement intersection F plus mu star of A intersection E complement intersection F complement. Now replace A by A intersection E union F. Then if you substitute A intersection E union F in these three, now E intersection F is subset of E union F, so when you take the intersection you will just get back. So let me write that. So mu of A intersection E union F equal to mu star of A, correct. A intersection E union F equal to, so here I have A union F intersection A intersection F, so that will again give me mu star of A intersection E intersection F again plus mu star of A intersection E union F complement will just come back again, mu of A intersection E intersection F complement, then mu of A intersection F complement will be empty, so that mu star of empty set is 0, so that won't come. Similarly here you get mu star of A intersection E complement intersection F will come, but mu of A intersection no, this won't, this will come. For F, but when I put E here, E intersection E complement will give you empty set. So it's just these three terms. So now you see that these three terms here are precisely the first three terms here, and consequently I can write, so this implies that mu star of A intersection E union F equals mu star of or rather mu star of A is mu star of, the first three terms is mu star of A intersection E union F plus mu star of A intersection E complement intersection F complement. But that's very nice, that's mu star of A intersection E union F plus mu star of A intersection E complement intersection F complement is E union F complement. So mu star of A is equal to this, and this implies that E union F belongs to S bar. So it is closed under unions. So similarly, now we will do for the difference. So similarly, replace A by A intersection E minus F complement, which is A intersection E complement intersection F. because E minus F is nothing but E intersection F complement. So E minus F complement is E complement union F. Okay, so that is what we have. So now we replace it again in that relationship. So then you get that mu star of A intersection E complement union F equal to, so the you will get mu star of A intersection E intersection F plus, the second term won't come because you have E intersection F complement in this term here, and here you have E complement and F, which are the complement. So both terms will give you empty set, so that term will drop out, plus mu star of A intersection E complement intersection F plus mu star of A intersection E complement intersection F complement. So now you substitute these three in the values, so you get mu star of A equal to mu star of, for those three I will write A intersection E complement union F plus mu star of the one which was left out, which was E intersection F complement, mu star of A of intersection E intersection F complement. But that, what is that? What are these sets? This is precisely mu star of A intersection, we just saw this, E complement union F is E minus F complement, so E minus F complement plus mu star of A intersection, E intersection F complement is nothing but E minus F, and from this we deduce that E minus F also belongs to S bar. So you have that S bar is a ring. So now in fact we can prove much more than this. So next proposition, X non-empty set, H hereditary sigma ring, mu star outer measure on H, S bar equals mu star measurable sets. Okay, then S bar is a sigma ring. Further, if I equals 1 to infinity is a sequence of mutually disjoint sets in S bar whose union is E, and if A belongs to H, we have mu star of A intersection E equals sigma I equals 1 to infinity mu star of A intersection EI. So in particular, if A equals E, then you have mu star of E equals sigma mu star of EI, implies countably additive on S bar. So mu star becomes a measure there because it's countably additive, it is 0 on the empty set and it's non-negative. These are the three properties of a measure. So in particular, if you have that's why the so we have that S bar is a sigma ring and mu star is a measure, and we also so these are the two things. So proof. So we already saw something about mu star of A intersection E1 union E2. So we use this relationship here. Mu star of A union F is E intersection F, E intersection F complement, and mu star of E complement intersection F. Okay. So mu star of A intersection E1 union E2, plus mu star of A intersection E1 intersection E2 complement plus mu star of A intersection E1 complement intersection E2. So then if E1 intersection E2 is empty, then what do you have? That E1 is contained in E2 complement and E2 is contained in E1 complement. So you apply all these three things. So mu star of A intersection E1 union E2 equals, the first one, E1 intersection E2 is empty, so the first term is 0. The second one is E1 is contained in E2 complement, so E1 is a smaller one, so that will give you mu star of A intersection E1. Similarly, the next one will give you mu star of A intersection E2. So by induction, for any n, we have mu star of A intersection union I equals 1 to n Ei equals sigma I equals 1 to n mu star of A intersection Ei. So now let us set Fn equals union I equals 1 to n Ei. Now we know that S bar is a ring. We proved this in a previous proposition, implies Fn belongs to S bar. Further, Fn is contained in E, and therefore this implies that E complement is contained in Fn complement. So we now have mu star of A. Fn belongs to, so this is not. So Fn belongs to S bar, therefore mu star of A equals mu star of A intersection Fn plus mu star of A intersection Fn complement. And A intersection Fn, mu star of A intersection Fn, we have already seen, this is sigma I equals 1 to n mu star of A intersection Ei, and Fn complement is a bigger set than E complement, mu star is monotone, so this is greater than or equal to plus mu star of A intersection E complement. Now n is arbitrary, therefore mu star of A is greater or equal to sigma I equals 1 to infinity mu star of A intersection Ei plus mu star of A intersection E complement. Now replace A by A intersection E. So then mu star of A intersection E is greater than or equal to sigma I equals 1 to infinity mu star of A intersection Ei, because I am going to take A intersection E complement will be 0. Okay, so that is that won't give you anything, and consequent, so this implies mu star of A intersection E complement is 0, and therefore you have mu star of A intersection E is bigger than or equal to just this, but by subadditivity this is greater than or equal to mu star of A intersection E. This is subadditivity. So this implies that mu star of A intersection E equals sigma I equals 1 to infinity mu star of A intersection EI, and this implies that mu star of A is greater than or equal to mu star of A intersection E, because that infinite sum is equal to that, plus mu star of A intersection E complement. And I already made this remark long ago that it is enough to prove the greater than or equal to inequality here, and therefore this implies that E belongs to S bar. So this implies that S bar is closed under countable disjoint unions. But any countable union by taking differences, we have already done this, can be written as a countable disjoint union in a ring. But S bar is a ring, and therefore, so this implies that S bar is closed under countable unions, and this implies S bar is a ring which is closed under countable unions, so that is a sigma ring. Okay, and we have also proved that equation which we wanted to. Okay, so definition: a measure mu defined on a sigma ring S of subsets of a non-empty set is said to be complete if E in S mu E equal to 0 implies F belongs to S for every F contained in E. So a measure is complete if you have a set of measures 0, then all subsets of that set belong to the sigma ring. Okay, so then it's called a complete measure. So we have the following theorem which we've almost proved. X non-empty set, H hereditary sigma ring on X, mu star out of the measure on X, S bar mu star measurable sets. For E in S bar, define mu bar of E equals mu star of E. It's the same, yeah, I'm just saying. Then mu bar is a complete measure on S bar. So proof: we already remarked that mu bar is a measure on S bar. So we already saw that, because here, so this is countably additive on S bar, that is what we saw, and therefore we have that it is a measure. So now let mu bar of E equal to 0. So this implies that mu star of E equal to 0, because it's the same thing. And now let E in S bar. So let A belong to H. No, this is not what we wanted to show. Let mu star of E equal to 0, E in H. Let A belong to H. Then you have mu star of A is mu star of A E, which is 0, plus mu star of A. By monotonicity, this is greater or equal to mu star of A intersection E, the first term. E is bigger than A intersection E, plus A is bigger than A intersection E complement. So this is true. So this implies that if mu star E equal to 0, this implies E belongs to S bar. Then F contained in E implies mu star of F is also 0 by monotonicity, and therefore this F also belongs to S bar. So this implies that mu bar on S bar is complete. Okay, so we say that so this completes the proof of the theorem. So we say that mu bar is the complete measure induced by the outer measure mu star. So our next step is clear. We know that if you have a measure on a ring, then you can have an outer measure in a very natural way, and then I know how to construct a mu bar. Now the only question is, are the elements of the original ring also in the hereditary sigma ring? Are they also in the, are they all measurable or not? So that is a question which we have to answer, and therefore once we answer that, then we will know how to extend a measure to something bigger. So we will do that next time.